Hello, everyone. The paper that we decided to use today for our research spotlight project is called Torpor, GPU enabled serverless computing for low latency, resource efficient inference. I'm Jennifer, and I will be presenting today alongside Navo and Thomas, and I'll be going over the motivation and the conclusion aspect of the paper. Navo will be going over the design, and Thomas will be going over the implementation and evaluation. This slide right here is basically, again, just a breakdown of who is doing what and who did what. And so we can move over to the next slide. So on this slide here, we just listed the authors and their affiliations. And we also included a link to the research paper here. So you can go and look at that, and if you want to read more into Torpor. And so, yeah, we shall move on to the motivation part of the paper. So why do we need a better serverless GPU platform when there is plenty of them out there? So I think basically the main question is, why does this paper even exist? Like, we already have serverless platforms. We already have GPU cloud services. So what is actually broken about it? Why is Torpor a thing? And that is exactly what we are going to go over in the next slides. So the way GPU platforms work today is something called early binding. And basically, when you deploy a model, it gets locked into a specific GPU right away, and it just stays there. It doesn't matter if anyone's actually using it or not, it just stays there. And so with that, it creates this problem where if you ever let the GPU go, you get what's called a cold start. The paper quickly measured this in Table 1. When a function goes cold and a request comes in, the system has to spin everything back up from scratch. For ResNet 152, that's 8 seconds, and for BERT QAs, it's 11 seconds. If your latency target is like 100 milliseconds, those numbers just would not work. So to avoid that, platforms just keep the model on the GPU permanently. But with this, with them doing that, keeping the GPU up permanently, you've now totally killed the whole pay-per-use promise of serverless models. So users are usually paying for a GPU, for GPU use, and when you have something like this, you're essentially paying for something that is not doing anything. And that's the issue, and that is the core of what the paper is trying to fix. We're trying to fix the idea of, what the service list is actually promising versus what the reality is, which is we have a GPU that we're paying for and we're not utilizing it correctly. We're paying for something that we're most likely probably not using what we're paying for. So this is figure 2, and it's actually straight from the paper. The graph on the left is showing how often these inference functions actually get called. The x-axis is a log scale, so you can look at where most of the function lands. 85% of them get invoked at most once a minute. 97% get invoked at most once a second. So the vast majority of these models are basically just sitting there. But under early binding, every single one is holding a GPU full time. The graph on the right shows that even if you try to pack a bunch of models into one GPU to fill up its memory, the load is still really low at real world request rates. So packing doesn't fix it either. This paper calls this severe GPU underutilization and load imbalancing. It's wasteful for users paying for idle hardware and wasteful for cloud providers who can't make use of their machines. So, why do existing solutions fall short? This is from table 2 in the paper. Um, and this basically it basically looks at the existing systems and checks them against four things. It checks them against GPU pay per use, GPU efficiency, SLO compliance, and whether they need to know anything about the model internals. So if you look at the first few rows, Alibaba Cloud, Molecule, DGSF, all of those use early binding. So they all use early binding, and 3 crosses 1 check. They have 3 crosses and they have 1 check, which is the model agnostic. But that's literally the only thing that they get right. If you look at the Inference, right here, it has 2 crosses. Well, no, it has 3 crosses. And it's basically interesting because it was built specifically for inference and it does try to handle SLOs, but it still cold starts when functions are warm. So again, the whole 8 to 11 second delays thing that we talked about earlier is presenting in Inference. And it needs to look inside the model for profiling, which knocks out the last requirement, the model agnostics. And so then we have Torpor, and Torpor is the only one that checks all 4, and that's kind of the whole pitch for this paper. Torpor is the only thing that, again, is going to have the solution of the falling short. So based on all of that, the authors actually spell out 4 requirements for what real serverless GPU platforms needs, and they label them R1 through R4 in section 2.2. So R1, which is pay per GPU use, in the paper, essentially it's basically saying that you only pay when your function is literally running on a GPU, not when it's idle, and not when it's waiting. Given how expensive GPUs are and how bursty those workloads are, that matters a whole lot in terms of a pay per use serverless GPU. Then we move on to R2, which is basically GPU efficient inference. It's not about one function running fast, it's about fitting as many functions as possible onto a few GPUs as possible. That's what makes economics work for the cloud provider. Then we have R3, which is SLO compliance. Users need to be able to set a latency target. And in the paper's example, they say 99% of requests within 200 milliseconds. So they need to be able to set this target, and the platform has to actively try to hit that, not just kind of hope for it. It should be actively hitting that target. And then we have R4, and R4 is that the platform can't look inside the model. The reason is pretty straightforward. Enterprise models have proprietary code and data, and cloud providers just can't have access to that. So the whole thing has to work as a black box. Everything Torpor builds is designed around these 4 things, and Nabo is going to walk you through exactly how that works. So I'm passing it on over to Nabo. Thank you.
Hi, my name is Navadit, and I'll be going over the design and the main idea, and I'll be talking about the blueprint. So first, Torpor turns dedicated per function GPU allocation into a shared pool that is scheduled, swapped, and managed just in time. As you can see, the layout is right here. First, the late binding takes place, then the GPU pooling, then the fast swapping, then the smart policies, and then the SLO aware serving. From early binding to late binding, the biggest shift is architectural. The functions stop owning GPUs ahead of time. So as you can see two comparisons of early binding and late binding. Um, One model is pinned to one GPU even while idle. This has low utilization and idle costs and load imbalance. And then late binding models wait in cheap host memory and borrow any free GPU at request time, and it's pay per GPU use and has good pooling and better balancing. Now the architecture overview. Torpor inserts a control plane between functions and local GPUs, so any function can reach any GPU in the worker node. First, you can see the ingress request takes place, then it goes to the model repository, then the GPU executors, and then the controller scheduling plus memory. Next, the user functions still issue normal CUDA calls. Torpor then redirects those calls to whichever executor or GPU is best at that moment. So what happens when a request arrives? A single inference request triggers scheduling and then possible model movement, execution, and cleanup. First, you can see the exact steps. The request arrives, then it chooses a GPU and executor, loads the model if it's not resident, and then it runs the inference. And at the end, it will decide to either keep or evict the model. So, GPU pooling instead of one function per GPU. The pool lets many low frequency functions share a small set of GPUs. As you can see, this diagram demonstrates the GPU pooling and gives you a rough idea of how each GPU works with each memory request. How Torpor keeps latency low. It has three mechanisms which make flexible GPU access feel close to native execution. The first is asynchronous CUDA API redirection. The function code avoids frequent CPU GPU synchronizations by redirecting CUDA, and it calls asynchronously to the GPU executor. And the result is there's little overhead versus native execution for most models. Second, pipeline model swapping. It loads model chunks while execution proceeds and overlapping transfer and compute instead of doing them serially. The benefit and the result of this is the pin memory plus parameter grouping cuts out swap costs substantially. Next, it prefers NVLink for heavy transfers. When a model already exists on another GPU, Torpor swaps the GPU over to NVLink when possible instead of falling back to the PCLE. And the result is NVLink avoids it with bottlenecks, which protects tail latency. Next, models move between shape memory and fast memory. Torpor keeps inactive models in host memory and only pays GPU memory cost when a request actually needs execution. As you can see with this diagram, you can see how each auto model uh, behaves when each request comes through with the GPU in the host memory. Now, the pipeline swapping hides transfer costs. Instead of copying everything and then computing, Torpor overlaps the two. So at first, you can see the serial baseline with the copy model running the inference and then waiting for the next step, and then it'll be pipeline to the two steps, stream A and stream B, which overlap shrinks the visible swap penalty and protects tail latency. Now, the memory management without model internals. Torpor manages model movement across GPUs while staying model agnostic. So the first step is the learning footprint. During first execution, Torpor tracks the model's memory footprint and CUDA patterns. The future requests can reuse that pattern even when the model is moved. Next, it tracks the addresses across GPUs. The controller keeps a global view of where model blocks live and fixes memory references during execution, which has automatic relocation. Next, it manages CPU memory in blocks. Instead of repeated raw CUDA allocation, Torpor reserves memory early and reuses blocks to reduce allocation overhead and fragmentation. The runtime, sharing, or isolation. The key point is Torpor gets the benefits of model mobility without needing to inspect model layers or architecture. Why the design is model agnostic? The platform deliberately avoids reading model structure or requiring framework-specific annotation. As you can see what Torpor does not need, which is layer graph, operator semantics, custom model rewrites, and hand-tuned memory plans. But what it does need is memory footprint, request rate, model happiness, recent execution history. Now, policies that turn flexibility into SLO compliance. Late binding only works if the platform also decides who should run where and what stays in memory. First, the request prioritization happens, which has the user required request count to estimate which function still has a good chance of meeting its tail latency SLO. Then it prioritizes those requests. Next, the inference aware scheduling. It prefers the GPUs that already hold the model. Otherwise, it favors the GPU that swaps over NVLink and avoids scheduling multiple heavy swaps at once. Next, eviction guided by model heaviness. It does not evict purely by recency. It also looks at heavy models that are more expensive to reload, so eviction decisions consider future swap cost and bandwidth contention. The combined effect is more functions meet millisecond scale tail latency targets while the platform still minimizes GPU count. Next, the light and heavy models are treated differently. The scheduler distinguishes cheap to move models from expensive to move models. First, you can see the light models has smaller swap penalty, can switch GPUs more freely. Good candidates for aggressive sharing, boosts throughput under bursty load. And the heavy models has large PCLE memory cost, prefers GPUs that already hold the model, avoid repeated cold moves, protect tail latency by limiting contention. Runtime sharing and runtime isolation. Torpor can either share GPU runtimes for efficiency or isolate them for stronger separation. First, you can see the runtime sharing. It has multiple functions reusing the same runtime, less memory overhead, better aggregate efficiency, and ideal when strong isolation is not required. For runtime isolation, stronger separation between functions, useful for security operational boundaries, higher memory cost and sharing, still works within the same pooling design. How the design satisfies the platform requirements. First, the paper GPUs, GPU chosen only when request runs, and it idles, and the idle models sit in host memory. The GPU efficient inference, pooling, and sharing let many functions fit on a small GPU fleet, and the SLO compliance, late binding plus scheduling decide which requests still have a path to the deadline. And no model knowledge. Memory and scheduling decisions rely on behavior, not internals. Key takeaway. Torpor's design is simple to say, but powerful in effect. It keeps models out of scarce GPU memory until they are needed, then use a shared pool plus smart scheduling to place work on the best GPU at the best moment. And as you can see the steps over again from the beginning. Now I'll hand it over to how the implementation works.
Thank you, Navadith, for going over the blueprint. I'm Thomas Hanna, and I will be going over the implementation, so basically how the system was built. So for the first details, Torpor is a GPU-enabled serverless inference platform designed for low latency and efficient GPU sharing. It uses a GPU pooling architecture, where your inference functions can access any GPU in a local pool instead of being permanently bound to one GPU. Idle models are kept in host memory and are moved to GPUs only when the requests arrive. Torpor reduces the overhead with asynchronous CUDA API reduction, pipeline model swapping, and NVLink-based transfers when available. It also includes GPU memory tracking and block-based memory management, so no models can move across GPUs efficiently. So the key implementation idea is that Torpor avoids the normal serverless approach of keeping each model permanently attached to one GPU. So instead, it keeps idle models in cheaper host memory and only loads them into a GPU when a request actually comes in. So to make that practical, the system uses GPU pooling, fast API redirection, pipeline swapping, and efficient memory management. So here's some practical design choices. The Torpor system is model agnostic, so it doesn't require any access to model internals, so you can keep your model as proprietary. It supports runtime sharing for better efficiency and runtime isolation for stronger separation between functions. And for memory allocation, Torpor reserves GPU memory early and manages blocks internally to reduce allocation overhead and fragmentation. For scheduling, it distinguishes between light and heavy models to reduce expensive PCIe swaps and improves SLO attainment. So these design choices matter because they show Torpor was built for real cloud deployment, not just as a toy prototype. The model agnostic design is especially important because cloud providers, they often can't inspect private customer models. So this allows this Torpor to be able to use by many people. So next I'll go over the main results and the metrics from the paper. So here, the evaluation setup metrics. The authors evaluated Torpor on worker nodes with 48 vCPU cores, 384 gigabytes of memory, and 4 NVIDIA V100 GPUs. They tested 8 popular machine learning models and compared Torpor against native execution and INF-less KA in node-level experiments. In the cluster experiments, they compared Torpor with native, non-swap, and simple swap. So the main metrics they looked for were tail latency, mainly the 98th percentile latency used to capture worst case user experience, and SLO compliant functions, which are the percentage of functions whose tail latency meets the deadline, and GPU load, which is the fraction of the time the GPU is actively processing inference requests. So the tail latency is important because users care about slow requests and not just average ones. So that tracks the slowest request, which is better for knowing the worst case. And SLO compliance is the percentage of functions that stay within their latency target. And the GPU load tells us whether the hardware is being used effectively. So here are the results. One, Torpor keeps latency close to the native execution. So Torpor's GPU remoting achieves latency that is comparable to native execution, and in some CB models, it's even slightly better. And for the model swapping, NVLink swapping performs much better than the PCIe for heavy models such as BERT QA. And Torpor's pin memory and pipeline execution reduce swapping overhead significantly. So these results matter because the whole system would fail if swapping models into GPUs made inference too slow. So the paper shows that Torpor is still fast enough for practical use. And here are the graphs that they showed to support that claim. Torpor adds very little overhead. Late binding can still deliver the near native inference latency. For the table on top, the rows are the different machine learning models, and the columns are native with the ideal case baseline GPU remoting, swap PCIe, swap NVLink, which are just two other models. And the bottom left graph shows that Torpor has a much lower latency than the GPU Vert US. And also it shows that Torpor with batch increases the latency. I mean, without batch increases the latency. So Torpor with batch is much faster. And on the right, it shows the impact of optimizations on performance. So for result 2, this is the results that showed Torpor improved the GPU utilization and load balancing. For low frequent functions, Torpor maintains high throughput because it can keep many models in host memory and share GPUs at request time. So at 10 requests per minute, Torpor achieves over 10 times higher throughput than native. In a 4 GPU worker with 40 high frequency functions, Torpor achieves much lower GPU load variance than native. And tail latency stays around 35 milliseconds on all GPUs with Torpor, while native can reach multi-second tail latency because of overload and queuing delay. So this is actually one of the strongest results of the paper, in my opinion, just because the native binding leaves some GPUs overloaded and others underused. So Torpor works, can move around work dynamically, so it uses the hardware much more efficiently. And this shows that. Here's a graph to support those findings. On the left graph, the y-axis is the normalized GPU load, and the x-axis is the GPUs. The orange is Torpor, purple is native. So you can see that Torpor has an evenly distributed load across all the GPUs, and native has an uneven load. You can see here it's much more for here compared to here. So Torpor evenly distributes work across GPUs, which is improving utilization. And for the right graph, we have the y-axis, this is the worst case response time, and the x-axis is how many GPUs. And you can see that Torpor's latency is low and stable, around 35 milliseconds across all GPUs, but the native latency explodes on overloaded GPUs, as you see here. Because it overloads some GPUs, there's long queues and huge delays. So Torpor just balances the load, avoids bottlenecks, and has much better load balancing, which leads to dramatically lower tail latency. The next part is their third result, where Torpor meets more SLOs than baseline. So in node-level experiments, Torpor outperforms both native and INF-less KA in the percentage of functions meeting latency SLOs. Torpor can support 480 functions on a 4 GPU worker node while still satisfying that millisecond scale SLOs. In larger mixed workloads, Torpor still supports over 80% SLO compliant functions, even with 560 functions. And in cluster experiments, Torpor is the only system that consistently meets per function latency (SLOs) even with over 1,000 functions. So this is an important evaluation because the paper is really about serving many inference functions cheaply without breaking latency guarantees. And here's a graph to support those findings. Um, the graph on the left, the x-axis is the number of functions, the y-axis is the percent of functions meeting SLO. And you can see that Torpor maintains 100% through the whole thing here, through each number of function. Meanwhile, native and INFless um, either start at 100, like native, and then move down slowly, or never make it up there. And the right, Torpor is the only system that scales while meeting latency guarantees. So here's results 4. Torpor delivers the real production savings. So you can see how much you can save in production with Torpor. So Torpor was piloted, deployed on Alibaba Cloud. And the pilot system serves more than 150 users and uses more than 350 GPUs and handles up to 465,000 daily requests. So it reduced the user cost by 70% on average and reduces the GPU provisioning cost for the platform by 65%. In one real case study, Torpor reduced the total user cost by 84% without hurting end-to-end performance. This is a strong result because many systems papers stop at simulation or lab experiments, but Torpor actually tested in production, which makes the claims a lot more convincing. And in this graph, you can see the top is that here Torpor, the blue line, is the only system that maintains SLO guarantees at large scale. And the bottom here, bottom left, you can see that Torpor provides consistent and predictable latency. And on the right, Torpor achieves better load balancing across the cluster. So Torpor is not just effective in experiments, it also provides major cost savings in real commercial cloud settings. And now I will hand off to Jennifer to go over the strengths and limitations from the Torpor results. Thank you.
Alrighty, so it's me, Jennifer. I'm back to close us out. So now that we've seen how Torpor works and what the evaluation shows, I want to take a step back and think critically about what this paper actually gets right and where it falls short, and what the overall takeaway is. Starting with the strengths. So starting with the strengths, and there are a lot of strengths here. I would say the biggest one is that Topor actually got deployed. It's not just a lab prototype. It ran on real production traffic at Alibaba Cloud, serving over 150 users using more than 350 GPUs, handling up to 465,000 requests a day. And that kind of real world validation is rare in system papers, and it makes the results a lot more credible. Um, the system delivers a near native inference latency, even while dynamically swapping models on and off GPUs, which was the hardest technical challenge to solve. It supports hundreds of concurrent functions per node while still meeting millisecond scale SLOs. It's fully modeled and agnostic, so it works across different ML models without needing to know anything about them. And users saw around 70% lower cost in real deployment. That's not a minor improvement, that's a major one. Um, Taken together, Topor hits all four requirements the author set out with at the beginning of the paper, which is paper GPU use, GPU efficiency, SLO compliance, and model agnostic operation. And that is not something that is easy to pull off simultaneously. So, with that, I would say those are the biggest strengths of Topar. So now we go into the limitations. Um, the most honest one is model swapping overhead. Even with all the optimizations, pipeline swapping, NVLink, pin memory, moving large models between host and GPU under heavy load still adds latency. The paper shows that BERT style models experience more overhead than CNN models like ResNet, so near native latency isn't uniformly true across all model types. There's also a hardware dependency. The performance gains heavily rely on having NVLink, um, and so on systems without NVLink, everything falls back to PCIe, which is significantly slower. Not every cloud environment has NVLink capable hardware. Um, then there's model size gap. Uh, Again, the paper evaluates ResNet 152 at 1.6 gigabytes and BERT QA at 2.4 gigabytes. And from table 1, modern large language models are 10 to hundreds of gigabytes at the scale. At that scale, the PCIe bandwidth Torpor relies on for swapping becomes a much harder bottleneck. And finally, the evaluation is done entirely on Alibaba Cloud with V100 GPUs. And the paper doesn't claim to generalize beyond that, but it means we generally don't know how the system performs on different hardware or in other cloud environments. So we just go based off of what we know. And so to wrap up everything, Topar introduces a GPU-enabled serverless platform that tackles a real and well motivated problem, and which is the fact that existing platforms waste GPU resources by permanently binding models to GPUs even when they're sitting at idle. Um, by using late binding and model swapping, Topor keeps idle models in cheap host memory and only uses GPU resources when requests actually arrive. The result is near native inference latency, which is much better GPU utilization, support for hundreds of functions per node, and about 70% lower cost in real world deployment. The core takeaway the authors makes is that efficient GPU sharing is the key to scalable serverless machine learning inference. And Topor happens to be the one thing that demonstrates that it's actually achievable without sacrificing latency or requiring model specific knowledge. Um, so yeah, that's our presentation, and we look forward to all the questions and comments that we receive. Thank you so much.